Hi, this is Lecture 14, and we're talking in this lecture about the Deadbeat control quadratic program. So in this lecture, we're talking about the performance program and how to cast the performance program into a quadratic program. That's the purpose of this lecture. Again, we have this 2 degree of freedom structure. We have N1, N2, and DC that we're looking for by way of our controller, given a plant with numerator NP and DP and a reference tracking signal NR and DR. And again, for now, we're assuming that we're going to be using just a step input. So once again, the general solution to our Diophantine equations involve these polynomials V1 and V2. We've seen that the performance basically is associated with these two polynomials, and so we'll continue working with those. As I mentioned before, we may have what's called a performance program that can be written something like this. That is, you want to minimize something like the transient control energy subject to the overshoot less than 5%, settling time, say, less than 0.3 seconds, maximum control effort, less than some quantity. And again, these numbers are generally specified by the control problem that you're working with. Some control problems, it's okay to have larger overshoots than this, in which case you wouldn't have, you might either have a larger number or you might not even have a constraint. That may not be an issue. Settling times are often constraints, and control magnitudes are often constraints. And these two are often in conflict with one another in terms of if you speed up one, you require greater the other, and so forth. So basically, a quadratic program is a minimization problem that looks like this. So notice our performance program, we're going to minimize something like the transient control energy, and we have these kind of constraints. So these are constraints associated with our problem. And what we'd like to do is like to set them up into a problem like this, which is a standard optimization problem. And so there are standard optimization solvers for problems like this. Okay, and so minimize something like this, where you have something transpose something else, subject to a set of inequalities like this. Okay, so this is our quadratic program. Sometimes you'll see the quadratic program like this. Instead of having this is a vector quantity transpose times the vector. Here we have a matrix and another matrix that define our cost minimization. And again, we have a set of inequalities like this. So these two are actually equivalent problems if we let H equal A transpose A and F equal A transpose B, then these two problems are actually identical. Okay, so sometimes it's easier to set it up one way, but a solver may be given it in terms of another way, and so this is how we can relate the two problems. Okay, control energy. We talked about control energy. How do we evaluate the control energy? Well, the concept of energy is an important quantity in all kinds of practical situations, all kinds of considerations and systems. So if you have a signal, h of t, the energy in the time interval, the energy required from 0 to some time, tf, is the integral of the power. And so often, the power of a signal is given by its squared quantity. And so the energy then is the integral over the time interval. So that's the energy required in that time interval of the signal squared. So notice that when you square the signal, this quantity becomes positive, and so you're integrating a positive quantity, and so the overall energy will be a positive quantity. And so basically, this quantity will be large if this quantity is large, is either large or it is persistent. Okay? So you can actually have a large energy if you have a long time that you're considering and the signal is persistent in that entire time. That can also contribute a large control. All right, so recall that our control signal u of t is the output of a zero order hold. Okay, that is, it is piecewise constant. So we've seen that it's like a stair-step function, right? And so basically u of t is a constant in the interval between sampling periods. Okay, that's what this is. This is the mathematical way of describing that. And so if you let, for example, the final time that we're looking at, the settling time, be some integer times the sampling period, then the energy in the integral u squared dt. Notice that because it's piecewise constant, we can actually sum. We can actually sum this up, and the dt just becomes t. That is the sampling period. So in terms of a signal, notice that we're basically going to look at something like this. This is our transient control signal. Because it's piecewise constant, we just sum up these little rectangles. And notice that when we square it, it all becomes positive. So even though the original signal may have negative parts, when you square it, the whole thing becomes negative, and then you add them all up. Okay, so that's actually what's happening. And so it's fairly straightforward to compute the energy of the control signal. In fact, it's just this summation. It's the sum of the control signal components multiplied by the sampling period. Okay, and so if we want to minimize the control energy, we can minimize the control energy by minimizing this sum. Okay, which basically boils down to something like a least squares problem. Cool. We've already seen how to solve a least squares problem. So if we recall the vectorized form of our control sequence, of our transient control signal, the vectorized form, so this is the remember, when you have a finite settling signal, you have the transient portion and then the steady state portion. So the steady state portion is the part where it's just constant after that time. And here you had a term that was a constant, and then you had a term that was a function of the parameters of our polynomial v1. And we're using, again, the concept of the expanded matrix here. And so this is a vectorized this is an expanded matrix. And so this is just a vectorized version of that expression that we had for the transient control signal. And so the transient control energy then is the square sum of the elements of this vector. So it's t times u1 vectorized transpose times u1. So this is how we can express this sum. It's this vector transpose times itself. Okay, and so we see that vector transpose times itself is like this. And notice this looks very much like what we saw in our quadratic program. Indeed, very important. The one difference is that there's a sampling period out here, but notice that this is just a constant in terms of the sum. And so in terms of the values of v1, this constant actually doesn't affect where the minimum is, the minimizing v1. It only affects the overall final energy. It does affect the final energy, but in terms of the minimizing value, it doesn't affect what actually creates the minimum. Okay, so we're going to ignore that sampling period when we do this minimization. Okay, so we can minimize the transient control energy by appropriate choice of v1 this way. And if all we want to do, if we didn't have the other constraints, then we could solve the minimization of this problem using the standard least square solution. This is the standard least square solution. We take this matrix pseudo-inverse times this, and that's the star solution. So in the case of no other constraints, we're good. We have an exact solution to our optimization problem. We have an exact solution, and there it is right there. Boom. So if all we want to do is find the minimum energy solution, boom, there it is. In fact, since it's so easy to calculate this is often a great place to start in terms of looking for initial solutions. Okay, it's a great place to look. Well, given the matrices now A, B, C, and D, we're looking now to find an X that satisfies this kind of problem. So notice we have J is what we define as our cost function. The idea of cost is we want to keep the cost low according to X. Okay, and so if you think about what this is actually like a parabola, or actually in n dimensions it's a paraboloid. So you can think of it as like a bowl kind of thing, and there's a minimum down at the bottom of that. Subject to, and here we have some equality constraints. So if you have an optimization problem like this, then there is a nice handy solution for this kind of a problem. This kind of constrained optimization problem can be solved using, so in calculus you learned about the concept of Lagrange multipliers. Lagrange multipliers. So we can rewrite this constrained optimization problem. Notice here we have equality. We can write this constrained optimization problem into this unconstrained optimization problem, where we're trying to minimize with respect to x this quantity. So actually, even though it says x, it's actually x and lambda. So lambda is actually another variable that appears here. So if we had equality here in this optimization problem, then we have another way of finding an exact solution. Okay, and you can go through and actually figure out how that solution looks. But it turns out we don't actually have this problem. Okay, in general, we have less than or equal to inequality. This kind of a constraint optimization cannot be solved using Lagrange multipliers. It was right within our grasp. Well, it just means we need to pull out a bigger hammer. What's the bigger hammer? Well, we need to use something called the quadratic program. Okay, so the quadratic program says, given the matrices A, B, C, and D, we need to find x that satisfies this. So here we have less than or equal to. Again, x is unknown. We're trying to find x that minimizes this quantity and ensures that these conditions are satisfied. So this is what's called a quadratic program. Okay, this is a quadratic program. So what does the solution to this kind of a program look like? Okay, so recall the least squares problem. When you have a quantity like this that you want to minimize, notice that when there are no constraints, again, we have an exact solution involving the pseudo-inverse of A. Okay, so we have that. And if you apply now that minimizer, so that's the global minimizer, this is the cost that you get. Okay, so we have an exact value for the minimizer, and we have an exact value for the minimum. Okay, and so by way of example, let's suppose this is our A and this is our B. X in this case is two-dimensional. We can actually express it this way, or we can actually apply these matrices, multiply it out, and we get this. And so you can see it's a quadratic in x1 and x2. So notice that x, our unknown, has two variables associated with it. And so we can, again, plot a function like this with respect to these unknowns. And in this case, we get a three-dimensional plot, x1, x2 versus j. Okay, and so when we plot it, we get a paraboloid. Okay, that's a two-dimensional parabola or three-dimensional parabola. And on that paraboloid, we can draw the contour lines. Okay, contour lines are lines that correspond to values that are constant. Okay, so the values that are constant are these contour lines, and we can project those down onto this plane. Okay, so each of these circle or each of these ellipses corresponds with a level value. And so we can see that the minimum value is right here in the center, and then as you go further out, the cost increases. Okay, and so we can see in this case we have a global minimum. Okay, the global minimum of this optimization problem is located right at that point, and it's at minus a pseudo inverse b. So if you have just the simple least squares problem, we have a nice, elegant solution in using the pseudo inverse. So we have seen that already. Okay. Now, in our case, we may not have that unconstrained optimization problem. We may have a constrained optimization problem, in which case we need to use a quadratic program. Now, again, program here doesn't refer to software. It refers to a type of problem, an optimization problem. And this is a constrained optimization problem. Now, when you have a set of constraints, it's possible that no solution may exist to those constraints. Okay, in which case the problem is said to be infeasible. Now, it turns out that if a constraint optimization problem does have a solution for a quadratic program, it's usually unique. if there is a solution. Now, because of the nature of the constraints, we can't just take the derivative and set it equal to 0. Well, you kind of can, but you have to be, it's not that easy, okay? It's kind of tricky to solve quadratic programs. But let me give you, and so what I want to talk about now is a little bit about the solution of quadratic programs and what the factors involved with the solution of quadratic programs and how that looks. So because it's a standard optimization problem, there's a lot that's known about it, and there are some elegant solutions. Software exists to find solutions or to tell us if there is no solution, if the problem is infeasible. Okay, so it's like, oh, dang, no solution. Well, sometimes knowing there is no solution is helpful. Then you can stop searching. You don't have to keep searching if you already know there's no solution. So for example, suppose you say, I want to settle within 0.1 seconds and I want control magnitude less than 10. The quadratic optimization problem comes back and says, sorry, there's no solution to that. Well, then you just can't do that. Okay, so you quit trying and you have to do something else. You either have to say, okay, let me take longer to settle, or let me allow a little bit more control magnitude or something. Okay, and so if we can set up our control problems as quadratic programs, then there are nice handy tools. So let's look at a solution of a quadratic program. So suppose we have, so here are the A and B matrices that we had before in our previous example where we saw that nice paraboloid. And suppose now we have a set of inequalities. Let's say it looks like this. Okay, and so in this case we have our quadratic cost function and our inequalities. If we plot our inequalities, we might have something, again, the things that overlap. And so in this case, we have this triangle that represents the region of acceptable values of x1 and x2. Okay, so again, in this case, we're representing a problem that has two unknowns, which makes it easy to plot. Okay, once you get beyond 2 dimensions, it becomes very, it's not easy to visualize. And for 1 dimension, it seems trivial. So it's just helpful. Okay, because it gives us a sense of what's happening in higher dimensions, even though it's limited. Okay, so here's our cost function paraboloid with the contour lines. Okay, and here are the contour lines mapped onto this plane down here, and we also have mapped onto this plane our constraints and how the constraint set. So here's our constraint sets here, but notice the global minimum, the global optimum is not in the region of feasible values. So this region of feasible values is where we have to pick our that's where we have to pick our solution from. Okay, so we can't just choose a solution anywhere, and in particular, we can't choose that value. We have to choose a value in this set. Okay, so the solution to the quadratic program must be in the region of acceptable values. So a feasible solution means you have a solution within this set, value x1 and x2 that are within this region right here. So this guy over here is not in there, and that is very commonly happens in quadratic programs. So we have to be able to take it into account. So the solution to the quadratic problem is the value of x1 and x2 that has the smallest value of j that is inside this region. Okay, and so one way to see that is by looking at these contour lines. Another way of seeing that for this simple kind of problem is to take these constraints and project them upward and see where they slice into our cost function. Okay, so here we extend those constraints upward, and we can see how the solutions slice into our cost function. So I'm going to take this plot and rotate it. Okay, and when we rotate it, we can see that this plane here slices right through our cost function, and in the process, the intersection between this plane and our cost function ends up itself being a parabola. Okay, so this parabola itself has a new minimum. Okay, again, now if we were to look at this strictly from above, from a top view, we would see that these contour lines, the contour line that just barely touches our constraint set, is the point where the optimal solution lies. So it's the smallest cost that is in the set, and so it's the contour line that just touches our constraint set. And as you can see, there's a unique intersection point. That's the point right where it touches. Okay. Now, one way of finding that point is if you knew which constraint was binding or active, then you can restrict your attention to that. You can restrict your attention to the active constraint. So in this case, the active constraint is this one. In this case, it happens to be the line x2 is equal to x1. And you can discard the other sets, and now you can treat this as an equality. Okay, so if x2 is equal to x1, then we can plug that into our cost function. So here's our cost function. If we plug in x2 is equal to x1, this is what we get, which simplifies down to this. Completing the squares, we get this. And so notice that this is minimized when x1 is equal to 1, because then this term will go to 0. Okay, and so in this case, x2 is equal to x1, and so this is our optimal solution. x1 is equal to 1, x2 is equal to 1. So so because we knew which constraint was active, we could apply that and simplify our problem and then solve the simplified problem. Okay, so this is just kind of a picture of what's actually going on in the solution of the quadratic program. Okay, so in MATLAB we have the command quadprog. Okay, so this is part of the optimization toolbox within MATLAB. So it's possible you may have a version of MATLAB that does not have the optimization toolbox, in which case you would not have this program. But it's available for us. Now, what does quadprog do? Well, first it checks to see if there's a non-empty feasible region. It checks to see if the least squares global solution is in the feasible set. If it is, if the global solution is in the feasible set, then done. That's the solution. If not, then it checks which inequality is active and sets the inequalities to equalities, and thus in the process it eliminates variables, simplifying the problem. It then becomes an unconstrained problem that has a global minimum, and then it solves that global minimization problem. So it does all of this for us, so we don't have to. Okay, yes, so we use that. So here's an example. We have a system, and we have a sampling period, t is equal to 0.1. We're going to follow a step in unit step reference. We want to find a controller that satisfies this performance program. We want to minimize the control energy, subject to the control magnitude being less than 5 and settling time as small as possible. So we're actually minimizing two things, control energy and settling time. Okay, so now settling time we can work with by adjusting the number of steps to settle. Okay, so recall that the control magnitude constraint and the settling time constraint are often in conflict. When both are given as constraints, we seek to find the smallest settling time that ensures the control magnitude constraint is satisfied. So when we take the H transform of our system, this is what we get. Here's our reference signal. And when we compute the minimum order solution using d(2), this is the solution that we get. So in general, you don't get nice integers. And our steady state value in this case is 0. And our U1, our transient control signal, is given by this expression. Okay, so our U1A is given by this vector. Notice that all of these magnitudes are greater than 5, which means that we cannot have V1 equals 0 and still meet the control magnitude constraint. So in this case, we let V1 be a constant. Okay, see what happens with a constant. So in this case, V1 is just a constant. We multiply it all out. We collect coefficients in Q, and we look at these coefficients in Q, and this gives us, we can check the control magnitude constraints. Okay, so now we can look at when, for what values of v1 each of these coefficients is less than 5. So we look at these inequalities. So this inequality, notice all of these inequalities are only a function of v1. So this says that v1 must be in the set between minus 13 and 23. This inequality says that v1 must be in the set between 10 and 13. This inequality says that v1 must be between 3.8 and 7.6, and this inequality says that v1 must be between minus 6 and 6. So we have those 4 inequalities, and if we were to graph those, we would notice that this one here is S1, this is S2, S3, and S4, and we notice that S2 and S3 do not overlap, and S2 and S4 do not overlap. Therefore, there is no value of v1 that satisfies all 4 inequalities. If I get a v1 that satisfies these 3 inequalities, this inequality will not be satisfied. Okay, so we will not have a control magnitude less than 5. So what this tells us then is our problem is infeasible. Okay, so no overlap. The problem is infeasible. That means v1 cannot just be a constant. So we move up from a constant. We move up to v1 being have a constant term plus coefficient times q. In this case, this becomes our v1, our u1. This becomes our u1b, u1a, u1b, and so here's our unknowns. The control magnitude constraints say this. These are the 2 control magnitude constraints. In vectorized form, it's all this. And if we plot those bands, we see that we have an acceptable region in here, right in here. Okay, and so if we look at the cost function, this is our cost function that we get from this, and if we plot the contour lines of that cost function, this is what we have. Okay, so here's our acceptable region right in here. There's our global optimum. Okay. If we zoom in, we see that there's our global optimum there, and here's our region of acceptable values. Okay, so our global optimum is not in our region of acceptable values. If we look at the contour line that just barely touches this, our constraint set, it's right there, and so this is our active constraint. There's our optimal x star, so we can see it's roughly 5.4 something and 13 point something. Okay, so our active constraint then is this: v10 is greater than or equal to 13.4195. So we use this equality, because that's the constraint set. So on the boundary of that constraint set, we have this, and so if we let v10 equal to this number exactly, then the cost becomes a function just of v11, and if we complete the square, this is what we get, and so this is our optimum solution. Okay, we plug that in to our controller, so this is our controller, n1. Okay, and we go through and we use the following Simulink diagram to simulate our system. And we simulate, and indeed, we have success. That is, we have control magnitude less than or equal to 5. In fact, it's equal to 5 right here, and it's greater than minus 5 here. And so we've solved the problem. Yes. Okay, so we were able to do this with the first order, with v1 being a first order polynomial. Notice we didn't say anything about overshoot, so we do have overshoot here that was not taken into account, but it works okay. So we have solved the problem. Now, suppose we had gone to a higher order solution. For example, suppose we wanted to go up to, say, v1 is a 200th order polynomial. Well, as you can tell, that's going to be a bigger problem to solve. Clearly not something we can just look at by plotting like this. And so that's where we would want to use something like MATLAB's QuadProg okay, which again solves this kind of quadratic optimization problem. Now, in our case, this is our quadratic optimization problem, right? This is U1 transpose times itself. And so when we expand it all out, this is what we get. And so H becomes this, and F becomes this. And so so that's what we use. So here I want my system to settle in 0.5 seconds. And it's going to do that in 200 steps, which means my sampling time is really small. So the reason I'm doing this, I want to see what does my solution look like if I let my sampling time be really small but still settle in the same time. Okay, so the number of steps to settle is quite large. Okay, so here's my plant, the discrete time model. Here is my my minimum order solution. So to find U1A, I can find using this command, the deconvolve of den P with 1 and minus 1, which is kind of an interesting thing that you can do. So the deconvolve is like dividing, polynomial division. U1B can be found by using the expanded matrix of den P, and this is how much we need to expand it by. It's actually the NS is the number of steps to settle, which in this case is 200, minus 3. So anyway, that's what we need. And so U1A then becomes this quantity and padded with zeros, so that it is the same length, that it has the same number of rows as this matrix. Okay, and then we divide by the numerator of the plant evaluated at 1. Okay, so this is U1A. So we formed U1A, U1B. From that we can form C and D. These are the matrices that we need for our constraints. H and F are needed for the optimization part, and then we can use quadprog. Oh, I had something else there. I don't know why I had that. Anyway, here's quadprog. And so what is quadprog? It returns V1, the V1 that we need. And so the numerator that we need then is related to V1. And so here's what we need. And then we need to pad it with the correct number of zeros. Okay, so anyway, so this is the overall. So we have the original, the minimum order solution that we need to add to this. But in order to add that, we need to make sure that they add compatibly, because again, these are vectors. And so this has a certain number of coefficients, and it needs to add with this, which is in general will have a different number of coefficients. In this case, a lot number of coefficients. Okay, so that's what we have. So now if we take this controller, the controller num1, and then the num2 and den C, the minimum order num2 and den C, then we get this response. And so here what we see are actually the response of the system when we used sampling period 0.1 and took 5 steps to settle, and 1 over 400 and take 200 steps to settle. Okay, this bluish response is the response we get. And so we notice that the two have a very similar shape in terms of their overall shape, and we notice that this blocky one basically follows the same path. This other one is a little bit smoother and has a kind of a parabolic shape to it, which is common when you're optimizing quadratic type programs. But we see that the output response is almost identical, and the other responses are identical. So in this particular case, there's really no advantage to using a small sampling period to solve this problem. Okay, so the cost also of using this high order controller did not help the problem much. So we now have a tool to actually analyze a problem like that going to a higher order solution didn't help the problem. So in the spirit of KISS, Keep it simple, stupid. In the spirit of that, we would use the low order controller. So this is the quadratic program and how to use the quadratic program to solve our optimization problem, our performance program. Thanks for watching.